Hey everyone, today we'll be going over LeetCode problem 55, Jump Game. This is another problem off the Blind 75 list, which is a list of problems commonly asked during technical interviews. In this problem, we're given an array called nums, which contains integers. And initially, we are positioned at the first index of this array. Each element of the array represents a maximum jump length that we can do from that position. So we have here, for example, a nums array. And we have this array which is filled with 5 integers. Our goal is to reach the end of the array, so the last index, which in this case is index 4. And what we want to do is return true or false based on whether or not we can reach this last index. So our first number is the number 3, and this means that from index 0, we can make a maximum jump of 3 positions, meaning we can jump 1 position to index 1, we can jump 2 positions to index 2, or we could jump 3 positions to index 3. We have here a decision tree, which also represents these possible choices. And this decision tree would be our brute force way of approaching this problem, where we find and take into consideration every possible jump that we can make. So we see even in this tree, we can start off from index 0 and go to index 1 if we make a jump of 1 in length. We can go to index 2 if we make a jump of size 2, or we can go to index 3, just like represented in these arrows. Now from index 1, we see that we have a jump of length 2 max. So we know that from here, we can make a jump of size 1 going to index 2, or a jump of size 2 going to index 3. And we see that this is also represented in our decision tree over here. Now from position 2, we see that we can make only a jump of size 1. So from here, we could only make a jump of size 1 to index 3. When we reach this part of our decision tree here, we see that we have reached index 3. And from index 3, we have an integer 0, meaning that we cannot make a jump from this position. Therefore, when we reach index 3, we can never reach index 4, which is our actual objective. Therefore, reaching index 3 is a dead end. We also saw our other case, where from jumping from index 1, a length of 2 also leads us to index 3, so we know that this is also a dead end. Same here when we jump from index 0 to index 2, and then from index 2 to index 3, as represented here in the decision tree, and this is another dead end. And we also saw that we can jump from index 0 to index 3 directly, and this is another dead end. So because we can never reach our goal, in this case, we would return false. However, from this tree, we see that we are doing some repeated work. If we analyze 2 of the subtrees, for example here, which has 2 as the root, and here, which also has 2 as its root, we see that we're doing repeated work. Therefore, the solution could be optimized using dynamic programming. Say, for example, we create a dynamic programming array. We could then store in this array dp of 2 to be equal to false. So when we get to this index 2 again, we do not have to repeat the work. And we already know that we have returned false for that position specifically, and move on. The decision tree itself would be approximately an n to the n time complexity solution, but with the dynamic programming, it could be optimized to O of n squared. However, we could also use a greedy approach to solve this problem in a linear time complexity, and I'll show you how to do this, and we will code that solution up. I have here to the right another example for us to go through. This time we're going to use the optimal greedy approach, which has a linear time complexity. What we're going to do this time is instead start from the back of our array and move slowly towards the front. And at each position, we're going to see if from here, from this current index, we can reach our goal. So we're going to start from the end and see if from the end we can reach our goal, which is in fact index 4, which is this current index that we're looking at. Therefore, from the end, we will always be able to reach our goal. We would then move on to index 3. So our goal, however, remains at index 4. From index 3, then we're going to see if we can reach our goal, which is index 4. From index 3, we can make a jump of size 1, meaning that from index 3, we can in fact reach our goal. Therefore, what we will do is move our goal now to index 3 itself. Because if from index 3 we can reach index 4, our goal will simply be to be able to reach index 3. We then go to index 2 and see that from index 2, again, we can make a jump of size 1, meaning we can reach index 3, which is our current goal. Therefore, again, we can move our goal up by 1 position because we can, in fact, reach our goal from index 2. So our new goal will be to simply reach index 2. Now from index 1, we again see we can make a jump of size 3 max. However, we only really need a jump of size 1 in order to reach our current goal. So we can reach our current goal, which is index 2, and therefore, again, we can move our goal up by 1 position up to index 1. We now reach index 0, and we see that from this position, we can make a jump of max size 2, which is more than enough to reach our goal, which is currently index 1, and therefore we can move our goal up from index 1 to index 0. Once we are done going through this array and have gone from the end to the front, we will return true if our goal is currently index 0. In this case, we have moved our goal successfully up to index 0, so we will in fact return true. I'm going to be coding up this solution for you guys because it is linear in time complexity and constant in space complexity, so it's the most optimal solution possible for this problem. And before going on, I just wanted to point out for you guys that in this case of the first example, we would have our goal initially set to index 4. We know that from the last index, we can reach the last index itself, so we know that we can reach the goal from here. We would then go on to index 3 and see that from index 3, we can make a max jump of size 0. So therefore, we cannot reach our goal, which is index 4. So when moving on to index 2 and analyzing that index, we know that at this point, our goal would still remain at index 4. We have not shifted our goal up. From index 2, we can make a jump of size 1, which is enough to reach index 3, but not enough to reach our current goal, which is index 4. Therefore, we would continue on to index 1 and still try to reach our goal, which remains at index 4. From index 1, again, we'd have a max jump of size 2, so we would be able to reach index 3, but not index 4. So we would then move on to our first index, index 0, and our goal would still remain index 4. Now from index 0, we would need a jump of size 4 to reach our goal. Its jump is of size 3 max, so we would have finished this algorithm and reached the front, and our goal remains at index 4. It has not moved all the way to the front, and so because of this, we would return false. Now we're ready to code up the solution. We're going to start off our code by initializing our goal to be equal to the last index in our array. Then we're going to iterate through our array, and we're going to iterate from the end to the beginning. At each position in our array, we're going to check to see if our current index, our current position, plus our max jump length, which is the integer we have at this position, is greater than or equal to our goal, meaning that we can reach our goal from that position. And if so, if this is true, then we can move our goal up to be equal to our current position, which is the current index. Once we're done iterating through this array from the end to the beginning, if our goal is equal to 0, then we can return true. Else, we know that we have not been able to reach the end from the beginning, and so we can return false. Let's make sure this runs. And we see that it works efficiently. Thank you so much for watching this video. If you enjoyed it, please like it and subscribe to my channel. I'll see you on the next one.